Hey guys, this is Professor McNeil again, and this time I want to talk to you about the X-ray tube, which is Chapter 5. This is all information that you're going to need to know in Module 1. So let me just go over some of these things briefly with you. Probably not as in detail as I did in Chapter 1, but still going to be some information that'll be useful to you. And like before, I want you to know that this information is from the textbook. And so like these objectives come from the textbook, not necessarily the module itself. And what Chapter 5 does is take a detailed look at the X-ray tube. The most important thing is understanding how it works and how it works safely and competently so that we as technologists can extend the life of that tube. These tubes are not cheap, and if something happens to one and it has to be replaced, we're talking a lot of money. So we're going to be talking about the construction, the purpose of the housing, then we're going to talk about the parts of the tube, then we're going to talk about the operation, the anode, along with the anode, the line focus principle and the anode Hill effect. Then we're going to talk about the cathode. And then I'm going to help you trace the path of electricity through the X-ray circuit and the tube, connecting all of it to the operating console. Then I'm going to briefly mention the rating charts and the cooling charts and the housing cooling charts. Probably not something that you will have to use, but you need to know about them. And then we're going to talk about safe X-ray tube operation and extending tube life. First thing is, this chapter examines the X-ray tube itself, talks about its construction and how it works. The sole purpose for manipulating electricity in an X-ray circuit is to create the environment in the X-ray tube necessary for X-ray production. The need for the radiography to understand the tube is twofold. First, you have to know the basic understanding of how the tube works to competently and safely formulate exposure techniques. Now, we are going to talk about exposure techniques later, but this is how you start that. And by doing that, we minimize patient radiation dose. Second, this understanding is critical to extend the life of the tube and avoid damaging it. And we're going to talk about each part of the tube in the next few slides, and then how every selection of the console panel actually helps you to use it appropriately. The safe operation and proper maintenance of the X-ray unit rests with the radiographer, and then appropriate and operation and maintenance of the X-ray unit stems from the knowledge of how it works. So when we take the tube itself, and this is the X-ray tube, this nice little thing right there. So let's go into it further. There's something called a tube head assembly. So this is the housing. This is a tube head assembly without the collimator. So if you've been to lab or if you're about to go to lab, coming right off of here will be the collimator where you can actually open and close the shutters to the specific size of the image that you need to capture. So this is with that taken off. The assembly is composed of the protective housing, and then the tube is inside of here. Okay? The protective housing is the general construction is what we're going to discuss first. And so the tube is in a protective housing that provides solid, stable mechanical support. It's lead lined and it's metal. So not only does it have an electrical insulator and a thermal cushion for the tube itself, it also keeps the X-rays from going outside of where it needs to be. X-ray production itself is rather inefficient, and a lot of the electrical energy that goes into it is converted to heat. The reason this is made out of metal around this housing is so that it has an oil bath in there and some cooling fans that help dissipate the heat away from the tube, and that in itself protects it from thermal damage. You know, we talked about before thermal energy. The tube is immersed in the oil bath, and that draws away heat, and then the fans inside of there actually circulate air. That also helps dissipate heat. Because of the large current and voltage needed to produce X-rays, electrical insulation is necessary. So you should be able to touch this whole tube assembly and not worry about getting your hands hot or burned or anything like that, but it also keeps down the possibility of electrocution. There are two large cables that enter the housing and are securely attached to the tube through special high voltage receptacles. And if we go back to this image right here, that's where these two tubes go through. And then from that, the X-rays are produced and travel in one direction through the collimator to the patient and to the image receptor. So here are the reasons we have the housing. It provides a solid, stable mechanical support for the tube. It's an electrical insulator. It's a thermal cushion, and it absorbs most of the leakage radiation, reducing it to less than 100 milliröntgens per hour as required by regulation. So just so that you understand, we will eventually talk about how much radiation is produced every time you take an X-ray and what your steps are to make sure that you're not using too much. So that's all the reasons for having protective housing. Here's the construction. This image is in your book so you can know, but just like that piece of metal that you saw earlier, here are those two connectors. Here is where the useful beam comes out, and that's where your little collimator box attaches. This is the glass envelope of the tube itself, and this is where the window of the X-ray beam comes this way. If we did not have this metal housing around it, all of these little squigglies of leakage would be coming out. So it gives you an idea of where everything sits in there. Another thing about the housing construction, there's two notes of caution. If we did not have the housing and then the oil that's in it, then it would be hot every time, if we used it more often. And it's likely to occur more if there's fluoroscopy installed and if there's a permanently installed unit, which that's with fluoroscopy because they're under the table. And another reason for doing that is because if they were up top when we were doing fluoroscopy, it may be harder to keep them cool. And then the second reason is these high voltage cables. And so when you see this right here, this is not a handle. This is a cable. See where I'm pointing to right there? That is going to the electric box. And so this is not for you to grab and pull it around with. That is to stabilize the machine, and that's where it's going to get its electricity too. So when you grab it, you should be grabbing these handles out here, not anywhere else. So don't grab the cables when you want to move the tube, and don't let the patients grab the cables. Sometimes your patient will say, I've got to get up, and they just start reaching. And if these cables are hanging down a little bit, they'll want to grab them. They've actually gotten better over the years about making these a little different, where they go upwards instead of hanging down. So that's a really good thing. So the X-ray tube itself, pretend like this is a generic tube right here with the glass, and it's an electronic vacuum tube. And within the tube, no matter what brand you have or what type of X-ray unit you have, they have some of the basic components in common. And we're going to talk about the design used for general medical radiography. So, as I stated earlier, it's an electronic vacuum tube. It has an anode, and I'm going to point, here's your anode. It's got a cathode, here's the cathode, and it has an induction motor right in here. And it's all encased in a glass or metal enclosure. So this is the glass, and then it's got that big metal thing around it. So this is probably the first time you've heard this, but the word anode means positive end of the tube, and cathode is the negative end of the tube. The anode has a target and the induction motor. Half of it's inside and half is outside the protective enclosure. And we're going to talk about those individually in just a second. But the cathode is what has the focusing cup and the filament right here. So anode, big motor, cathode, filament, and focusing cup. The main purpose of the X-ray tube or the whole enclosure is to maintain a vacuum, and because of the production of X-rays in between the filaments and the anode target, if there was any air in there, then the electrons would contribute to the electron stream, and that would cause what's called arcing, A-R-C-I-N-G. And, oh, it's right there. So electrical arcing, we want to prevent that because that would damage the tube. There's two different varieties. You can have the usual is a glass envelope, and it's made of borosilicate glass, which is another nice word of Pyrex, because it's heat resistant. But as the tube ages and we use it more often, there's tungsten deposits that happen on the inside of that glass, and that can actually cause them to become bronze colored. And then those tungsten little pieces can start causing arcing again and damage. And then there's the metal envelope variety that has a constant electrical potential between the electron stream, and that avoids the arcing problem and it extends the tube life. The difference is when they have the metal type, they're much heavier, and so those could only be used in really stable permanent positions and tables. Both of them have a target window, which is where the X-rays are to exit, okay? So the X-ray that leave the tube all come from the same place. Now, it is usually about 5 centimeters square, and it's somewhere on the enclosure that's thinner than the rest of it. And that thin section reduces the amount of absorption so that more X-rays are actually sent outside the tube. So here's the target window, what we're talking about. So the target window is where the exit point of the X-ray is, so we can look right here. So this is, just pretend like this is a lead casing, however it's shaped. There's our glass. There's our anode. Now all of this is oil in here. And then here's your focusing cup. There's the anode target. So they're boiled off here, sent to the anode, and then the X-rays come straight down. And that's your window right there. And I've already talked about it as about 5 centimeters square, This is just another way to look at it. This is probably closer to the way it actually works. This is where those cables come in, and it keeps this leakage from coming out. Therefore, if something is broken in here, those X-rays can come out of there. So it's always checked. Here's our oil, here's the lead lining, and then here's our primary beam. So let's talk about the anode. The anode is the positive end of the tube. This is the target. The electrons are created at the cathode side, and then it sends it to the target of the anode, and when it hits that, the anode is well, there's two types, but we usually use a rotating type, and it is an electrical and thermal conductor, and they interact in some way, every electron that's produced. And then the rest of them is the continuous current flows. And there's the two different designs, as I kind of mentioned. But before we go any further, let's say here's the cathode making electrons go towards the rotating anode. They hit it and then go straight down through the window of the tube housing. Now, what is the anode made out of? It doesn't matter which type of anode you have. These are the 4 common materials. Now, I'm going to give you a little bit more information than just these 4 names, because you need to know their scientific symbol and their atomic number. It's very possible you may see a test question either in this course, in a later course, or even on your registry that only gives their chemical symbol. So if you didn't have chemistry before coming into this program, you might want to look it up again, and I believe there's a nice periodic table in your book. It's worth looking at. So here are the main ones. Copper. Copper is used as part of the shaft because it has excellent thermal and electrical conductive properties. Now this is only in the anode, okay? So remember that. Now, what you need to know about copper is, if you remember anything about chemistry, the lower the number means that it is it conducts. It does not resist. So the copper has thermal and electrical conductive properties. So it has a low heating point, which means it doesn't take much energy to heat it up. Then the next one that's used is molybdenum. I always like saying molybdenum. And it's used as the disc base because it has a low thermal conductivity. It slows the migration of heat, and it's a light but strong alloy, making it easier to rotate the anode. So this number is 42, so this is the place on the chemistry chart that you would see it, and its heating point is 95. So it's a little bit a lower thermal conductivity, meaning it's going to stop some of that heat. Then the next thing is tungsten. So as you notice, we're moving right on up the chemistry or the chemical chart. So this is the target material that it's coated with, and it's coated with tungsten because it has a high melting point. So just to give you an idea, is that tungsten can withstand up to 6,000 degrees Fahrenheit. Now, even here in Florida, when it gets hot, we should only hit about 105 degrees. So we're talking 6,000 degrees of heat, and that tungsten can withstand it, and then it makes the tube and the anode itself work a little bit better. So it has a high atomic number, 74, so it's moving on up the chart, and it helps the efficiency of X-ray. So this right here means it can withstand a lot of heat without any damage whatsoever. Now, with the tungsten, sometimes, and pretty much all of our newer tubes today, use something called rhenium. Now, rhenium is just one step above tungsten, but it is sometimes mixed with the tungsten so that it increases the capacity and the tensile strength, which means that it keeps it from getting hot and conform from the heat. So if you ever have melted a penny or something and you saw how it kind of gets wavery, it floats around, that's what would happen if you use just copper. So that's why you use all of these materials. So those things are very important to remember. So back to the two types of the anode. The first one is the stationary anode, and this is kind of a picture of one. This would be a stationary. This is an older one. This is an old tube. You sometimes still see this in dental X-ray units, but you're not going to see it in your typical X-ray and imaging department. The disadvantage is that it's just a tungsten button embedded in a copper rod. So this is copper, and then there's our tungsten right in the middle. And it's stationary because it doesn't move. Because the electrons always hit the same area, so if you think about the tube and they're bombarding the target right here, then that right there is going to start bending because of the constant bombardment. And it will build up heat, and then it damages the tube. And because of that, we can only use certain techniques. You cannot get up really high on the kVp or the mass, therefore you can't take a lot of X-rays. That's why it still works in a dental unit, because it doesn't take very much to X-ray our teeth. So the one that we use more often is the rotating anode. That's what we use in today's tubes. And it has a rotating disc. So here's the disc right here that constantly rolls around, and it's made of molybdenum, and it's coated with tungsten. And remember, it can have some rhenium in there too. Now it's still on a copper shaft, and it spreads the heat produced. So as the electrons hit it, it doesn't just hit one target, it spreads it around here. So rotating means it's not hitting the same spot every single time. The purpose of it to rotate is to spread the heat, and instead of it going in the same spot, only a little bit. Now this is where we have something called a focal spot or a focal track, and the heat building up is going to be around the entire circumference of that spot. So it just, number one, it increases the heat load capacity so we can use higher techniques, get more exposure, and it can withstand a lot more heat, so it's not going to melt on us. So with this rotating anode, is rotated using an induction motor. Now, I threw out just a YouTube video about how an induction motor works, and I think it's worth you going and looking at it. I mean, hey, YouTube videos are always fun. And with that, there are two major parts. There's called the stator, which stabilizes, and then the rotor, which moves. So all of this is the anode, but this is the rotor, and then there's the stator, and all it's doing is two sides to it holding it still. There's a little stem, and then there's your rotating disc right there, and that's made out of the tungsten and rhenium. And the rotor itself is made of iron core that is embedded in copper, surrounded by coils located in the stator, but still within the enclosure. The rotor does not touch it, nor is it supplied with electric current. All this is doing is this is turning while these hold the whole tube itself stable, okay? So just know that. With an induction motor, it operates on something called mutual induction. So as one thing moves, everything moves. If you actually watch the video that I put out there, it has this same image right here, and you'll see it in motion. So as this moves, then that moves, then that moves. So the word induction means to create something else or to induce. And so one pair will move, the next one pairs, and it just keeps on going. The most important part of the induction motor is that it actually is capable of 3,400 revolutions per minute. And then if you have a specialty tube for other types of imaging, they can get up to 10,000 RPMs. So the more it moves, the more heat it can disperse, and the better your imaging will be. This is just another induction motor. So here's the first sequence, then here's the other, and then there's your stators that are keeping it from spinning off into space. So it allows for the rotation of the anode in a vacuum, and I've already told you about how fast that they can actually go. Now, something else that you need to know is that the anode itself, so go back to that image that we saw, you have the stators, the rotors that are moving, and a little stem, and then this is the part that goes round and round. So here's, by layering it, it will actually withstand even more heat. Little bit of tungsten on the top, mostly molybdenum, and then you can have graphite right here that actually attaches it to the stem. The target itself is, go back and discussing this target. So this is all copper. Here's the molybdenum or graphite base. They can be either a 2-inch to a 5-inch disc, which is the focal track. Here's the speeds that they can go. And then here is one more word that I've not shown to you, but sometimes in some of the newer stuff they're using rhodium. So rhodium is something else that could be added, but rhodium, just so you know, is pretty expensive. So they don't put that on a lot of things, but this is what it looks like right there. As the anode spins, electrons continually hit the track labeled W, so right there. And then the smaller the focal spot, the better the resolution. Now, we're not going to get into resolution right now, but eventually you will. Resolution in general just means a good image, and the sharper the image. So whatever that tube can have to give us a better image, the better off we are. Okay? So now let's go to the line focus principle. Now we're still talking about the anode. So here is a basic, now we've squared it off instead of making it round. Here's your target angle. Here's your electrons coming from the cathode, and we'll talk about the cathodes in just a second. And it's sending these electrons across here to hit the anode. Then, as it comes down, it goes straight down out that tube housing. Notice the size of the electron beam size, and then the effective. So what it actually hits is here, and that's the actual focal spot size, but what is actually coming out, or the effective focal spot size, is going to be smaller. And the line focus principle, you need to know just what that principle is. Angling the face of the anode target, a large actual focal spot size can be maintained, and a small effective focal spot size can be created. And you want that so that your image has better resolution. The actual focal spot is what's bombarded by electrons. The size of the stream depends on the filament, which is in the cathode. The smaller the stream, the greater the heat. So you want more or a larger stream to come so there's not as much heat, and then that way the effective focal spot is smaller on the patient's perspective, meaning the patient's not going to get too much X-ray. Now this is just one that's turned completely the other way. We'll talk about these degrees and target angles later, but here's your electron stream, focal spot size, actual focal spot size, and effective focal spot size, and it all works from the spinning target. Here's another. So if you have a 24 degree, look how this anode's turned. So we've got more of a steep angle, and with that, this is going to be a larger effective focal spot size. Anytime that the angle is less than 45, the effective will be smaller than the actual. Usually we have angles are 7 to 18 degrees for general purpose tube, and 12 is the most popular or the most common. The smaller the angle, the smaller the effective focal spot is, and that means that a large actual focal spot size dissipates the heat a little bit better, but it improves your image. This would be, you know, same size, but because this has less angle, this is a smaller effective, and this is going to give you a better image. So this is what we want to use whenever possible. Once you've read your book, and maybe if you have any questions about this, if you want to call me up, email me, whatever you want to do, we can kind of go into that a little bit more, but you can also work with this in your lab. So here's another effective focal spot. It's almost that exact same one, difference of a 15 degree and a 10 degree, but it gives you an idea. These are the same going across, but the smaller the angle, the smaller the effective focal spot. The smaller the effective focal spot, the sharper your image is. And these changes are not because of something in the tube. You have to select that at your operating console. So the angles are optimized for mammography, angiography, and general radiography. Each one of those is going to have a different type of effective focal spot. And the sharper the image, the better. And we'll talk about that more in the course that's coming up after that, which is called Radiographic Equipment and Acquisition. So now we're going back to the line focus principle. This is a balance between the heat area and the projected focal spot, and it introduces the anode hill effect. So go back here. Effective focal spot has to do with the line focus principle. So what it hits and then how it comes down is something called the anode hill effect. You can't see my hands right now, but pretend like I put them together and I'm doing this. Anytime you see a light coming out of a flashlight, what does it do? It starts at a point and it diverges as it goes out further. Well, that's what happens to our X-ray too. We intend for it to come out of the target window in one straight line. That's what we want. There's our central ray. But what actually happens is that some of this goes off to the side, and some of these angling off to the side are not part of our useful X-ray image. And so the angle causes the intensity to be less on the anode side because of the heel of the target. Therefore, the radiation intensity on the cathode side is always higher than the anode. But because the electrons on the anode must travel further than those close to the cathode, they have slightly lower energy than the cathode side of the X-rays. So that's called the anode hill effect. Now I've got a couple more images to show you that a little better. So here is the cathode side over here, and it's sending electrons, sending. And every time it hits, they are supposed to come right down. But the beam intensity is because more of the electrons hit on the cathode side. Look how many more electrons come out. We have 120%, whereas on the anode it's only 75%. And that's because they're absorbed in the target heel. So when we're The difference is you're going to find that we have different size image receptors. And not only do we have different size image receptors, when you collimate, that affects the anode hill effect. So the difference between a 14 and a 17-inch receptor means how much of that X-ray is actually going to where we need it to. So the intensity of the beam is less on the anode side. And I don't know if it helps you or not right now, but the one thing I learned in X-ray school, and people still say today, is always remember fat cat. So it's going to be fatter on the cathode side than it is on the anode side when the X-rays come out of the target. So because some of those that come out towards the anode, they don't have the energy to go anywhere, then they're absorbed in the heel, and that reduces the intensity. So notice here that the percentage, I've already shown you that, there's less here than there is over here. And it's going to be also make your image lighter on that side because there's fewer high energy X-ray photons. Now, when we actually had film screen, so we actually used a film, had to take it to a processor and develop it, it was very, very noticeable. With digital technology, which is what we have today, it's less noticeable, but it's still there. And we, again, will discuss that in your next course, next quarter, but it's something called dynamic range. And with that dynamic range, we can determine how much of a anode hill effect there is. So this is just one more way to look at it, is electrons hit the target, come down, less are on the anode side than are on the cathode side. Okay? Now, let's move over to the cathode. The cathode is the negative diode of the X-ray tube assembly. It has a focusing cup and filaments. The focusing cup is made of nickel, and it houses the two filaments, and then the filaments are surrounded by the focusing cup, leaving the front open and facing the anode target. So here's the cathode. Now again, this one's kind of flipped backwards from what we started with, but here's where they come from, and it hits the anode. So you have to understand, when these electrons come out, they're not hitting the middle of the anode, they're hitting right here at the bottom, and that's why it's important to have that rotating. And then this is a nice image of the rotor. Don't have the stators as well on there. So the negative side of the tube provides the source of electrons. The reason we have two different filaments is that we have one for a large focal spot. So guess what? It's longer than the small focal spot. And the smaller one is a little bit smaller. And with that, the differences are when you decide which particular image that you're taking, and we'll go into it in just a second. So when you have a dual focus tube, you have the two filaments, and that's when you have the large and small focal spot options. So most of them have two. The only time that you would find only one is in an older unit when it's just a non or stationary anode, and then these don't have a different size in them. So here is the right here, and the different filaments are in different sizes. So they're usually 7 to 15 millimeters long, 1 to 2 millimeters wide, and they're made of tungsten, just like we heard tungsten before, with a little bit of thorium added. And they're parallel to one another in the focusing cup, and they share a common ground wire. Now, the tungsten is usually just the majority of the elements, and it's only 1 to 2% of thorium added. And again, it's because of the high melting point. Thorium is actually radioactive, that is added to increase thermionic emission, and we'll talk about that again later. And the thorium, when we talked about the radioactivity, it's not enough to be concerned with, and it's inside that metal tube housing, which has lead lining in it too. So you're not going to get radiated from the thorium that's coming out of these filaments. Okay? The focusing cup is made out of nickel. And what have you noticed about this nickel? Even lower on the chemical spectrum than copper was. It surrounds the filaments, it faces the anode, and it leaves the front open so that the electrons can head towards the anode target. It receives a negative charge from the secondary circuit as they're boiled off, the electrons are boiled off. The size, the shape, and charge of the focusing cup affects how well it focuses the electrons. And all of this is taken into consideration when you're thinking about an optimal image. The focusing cup's function is established through something called electrostatic repulsion, and that means the negative charge is greater than the negative charges of the forces and the electrons together. And because of this, they repel one another and scatter as they're pulled off the filament. Now this will all make sense in just a second. So look right here. Here is the cathode. Here's our glass envelope. Okay? Here's our heated filament, and it emits the electrons by thermionic emission. Then they're accelerated by high voltage. So here are the filaments, they're excited, the electrons are sent to the target, and then they come right through here. So the filaments are connected to the circuit, the focusing cup is connected to the secondary circuit, the focusing cup receives a strong negative charge, and then it makes a cloud as the electrons are boiled off through electronic repulsion. When the filaments are heated, then they start to boil off, and that's what we call thermionic emission. You will definitely need to know what that term is and find the full definition in your textbook for that. The electrons hover around the filament called space charge because it has a negative charge and they repel each other. And then these electrons move in the tube at 1/2 the speed of light. So here is an example of the repulsion. So here's the electrostatic repulsion, spreads them all out, but that focusing cup actually brings them in and puts them in a controllable area. And that's what the purpose of the focusing cup is, because if not, they would be spread out like this, and then they would hit the anode target and we wouldn't get the same image that we need to. Here's just another example. Here's the cathode. Here is the shroud that is actually around it, and then there's the focusing cup. So this is a larger, this is a smaller, and so when you focus it, then it hits only here instead of way out here. So it keeps them together when it goes to the anode, and if it did not have a negative charge in the cup, then the electrons would be spread out everywhere. And when you look at this, these that are not hitting the target the way they're supposed to, we also call those extra focal radiation, and this is when they are off focus and these projectiles actually interact with the target, and then they start bouncing off everywhere. And these are off focus and they will not end up being a part of your actual X-ray image, but they can leak out through that window and cause damage to the patient that you have on the table. So it increases the patient's skin dose, it reduces the image contrast, which I know we're not into contrast yet, but that's whether your image is nice black and white or if it's a gray, kind of a muddled kind of appearance. So that's what this whole process is about. The cathode has the two filaments, makes the electrons. The focusing cup keeps them in control so that they go exactly where they're supposed to, and we don't have as many extrafocal X-rays. Now, this little section is important also because this is the operating console. Now, I just went out there and grabbed two different types of consoles, and with that, we're going to retrace the steps to the tube and then talk about how it actually works. So when you go to the console right here, you're going to set your KVP. You're also going to set your focal spots, small and large. There's your patient size. This one's a little different, KV, MA, and time. All of these different things have to be set, and then you use this right here. This is your button. You hold this with one hand and then you push this little lever down about halfway, and I'll tell you what that does in just a second, but that's what actually makes the exposure. What you also need to know, this one has it too somewhere, I think it's over here on this side, but on this one, look at this right here, I want you to notice that big red button. And with the two things here that's the emergency button. So if for some reason something went wrong with your equipment and you need to turn it off quickly, you hit this big red button. So nowadays they actually kind of cover it with something so people don't accidentally hit it, because if you did, then you've kind of killed the machine. You're going to have someone come back and reset it and all that good stuff. But those are some important parts of the operating console in addition to your KV, MA, and time. So the first thing that you do when you actually take an X-ray using an X-ray machine, at the operating console you select the desired exposure factors. So pick your KV, pick your MA. Before this quarter is over, you'll know exactly what I mean when I say that. And then you're going to pick your focal spot, and then, you know, whether you make it through, no matter how you select it, then it doesn't matter. Pick your exposure factors. Then you're going to do something called rotor up. So if you go back to this right here, that's what I mean by rotor up. You kind of push the button halfway, and then when it's first pressed, the electricity is diverted to the induction motor and it rotors up to speed. And then sometimes somebody may even say hitting the rotor. So when you do it, it's just, you know, you can hear the machine kind of rev up and the electricity's sent and it's ready to go, and then you push it on down completely. And when you do that, then the selected filament energizes and it goes zoom right out this way. So here's our focusing cup. It took all those electrons, squished them together in one straight line, and it hits right here, and then your X-ray comes out the bottom right there. So to initiate the X-ray production, you make the exposure, and then only last a few seconds, and it's actually probably in milliseconds. And then when it's pressed, the voltage passes to the step-up transformer and then into the capacitor banks and all these other terms we're not going to worry about right now. But you do need to know, let's go back here, rotor up, everything's ready to go, hit the button all the way down, it initiates the process, and then it goes through all these other things. And then here's your window, there's your hand, and then there's the film right there. So that gives you an idea of how it all works. And it's just in a matter of seconds, milliseconds. And we're going to talk about circuits and processes a little bit later. You do need to know about the voltage though. The voltage, which is current, passes through a rectifier bank before passing to the anode and cathode. So the anode is always positive, the cathode's always negative, and that means there's a potential difference between the electrodes. So when you have the prepping stage or revving up the rotor, some of the power is diverted to the filament, and then it goes to the step-down transformer. And so it goes through something called a rheostat. And so your rheostat is right here in the middle of it. Again, we will go into more detail about that later. For right now, though, I want you to know about this filament. The filament heats up, and it's a point of incandescence, which means it gets white hot. The electrons are boiled off by thermionic emission, and then the focusing cup forms them into a cloud. And then this cloud is something called a space charge. So with this space charge, then it takes it and manages it down into exactly where it needs to go. Once it reaches the size commensurate with current, then it's able to actually emit an X-ray. So there are three things that you need to produce these X-rays. So you've gotten up to this point. The first is a large potential difference to give the kinetic energy to the filament electrons, and that's with kVp. The second one is a vehicle on which the kinetic energy can ride, and then that is mass, which is a combination of milliamperage and seconds. So you have to have kV so that you have enough power to get through the body part you're X-raying. It has to travel there through mass, and then it has to have a place for interaction, and that's the anode. Now, Later we will talk about how KVP is processed, how mass is processed, but right now you know the cathode creates the electrons, you rotor it up, then you hit the button, it sends it to the target anode, and then it goes through the window down and x-rays whatever body part you have in the path. With that, as they penetrate the anode target, because of that potential difference, then you have electrons that interact with the atoms of tungsten that generate heat and x-rays. So you've got all of this coming out at one time. Now it says these electrons will reach speeds of about half the speed of light in a 1 to 3 centimeters between the focusing cup and the anode target. And because it goes from the cathode to the anode, it's a constant flow of electricity. As they penetrate the target surface, these filament electrons interact with tungsten. And the two different things that it generates are heat and x-rays. Okay, so we will go on with how it continues to go, but you've got the basic idea of how it starts out. There are several factors that shorten the life of an X-ray tube or damage it, and most of them have to do with the thermal characteristics. So we've already talked about the heat. Every time you take an X-ray, it's heating up, and that is within our control because we've set the factors. The frequent use of high exposure factors or long exposure factors can actually overload the filament, and by doing that, it can cause damage to the tube. What you also need to know is that if you heat it up by prepping the rotor, so if you're doing an X-ray, in today's world, it doesn't happen nearly as much as it did in my day, because we'd have to hold the patient, and then somebody rotor up and then say, okay, shoot, and then you have to hit the button. But just sitting there with it rotoring up, it's just like a car engine. If you just took your key and just let it go, but the engine's already going, and you hear that really hard sound, that's what would happen if you did that for too long. So you don't want to overload the filament. And that's what this is about, is quality control. Making sure you do it right, check all the boxes, and do it correctly. If not, then you have too much built up heat. And we have heat tolerant materials. We also have an oil bath, we have cooling fans, we have protective circuits. But if we use too much heat and build up that tube, then there can be a problem. And in case you don't notice, this is a big old ring of fire right here. Now, your machines that you work with should never have that type of radiation, but you need to understand that all of that can actually occur if you don't treat your equipment correctly. Modern X-ray machines have protective circuits that are built in, and it keeps you from using unsafe exposure techniques, and it'll keep you from actually overloading the tube. There were times in the past where you worked with a single circuit X-ray and it did not have a phased generator, and so if you took a chest and a flat and erect abdomen, you may have to actually let the tube cool down for about 10-15 minutes before you can do another X-ray. We don't have it that bad now, but we need to understand that it could if we were to use unsafe practices. Okay, our final part of this is something called charts. Modern X-ray machines have protective circuits built in that prevent the use of unsafe exposures and keeps you from overloading the X-ray tube. However, you need to know the tools that are available to safely and responsibly operate the machine. Those two tools are rating charts and cooling charts. To better understand it, let's just go back in history just a tiny bit. Prior to protective circuits, these charts were used to determine if a particular combination of factors was safe for a given tube. Similarly, cooling charts were used to determine the cooling time. When I just said you may have to wait 10 or 15 minutes. Now, you would actually need to know how long you needed it to wait before you could use it again. They were simple to use, and we actually had to use them on not a daily, but a regular basis. Today, they're still useful as a quality control tool, but that's about it. You need to understand what it is, and you may possibly see one later and say, hey, I don't know if using this technique is safe for this machine or not. And so it'll give you an idea if it's ready to take another exposure. So it gives you the idea if it's safe or not, okay? So a tube rating chart. There are three things that you look at. This is two different examples. So this maximum exposure time, and then over there in the seconds. We look at kVp, kilovoltage peak, milliamperage, and exposure time. So if you put your MA and seconds together, you get mass. Some use kilovoltage as the y-axis. In case you don't ever remember, this is always the y, and I do it like this. So if you make a line and then bring your y down, and then the x is across the x across. So kV and then there. This one is only for MA and seconds, okay? That's the two differences on these. And so with the milliamperage as the Y, the exposure time is the X, and the kilovoltage peak lines are the curves on the graph. So either way, in the first type, one uses kV, and then, here's what you need to know about it. Exposure time to plot a point on the graph. If that point is on or above the specified MA line here, so how much MA can I actually use? And then you plot it on the graph. And if it's above that kV, then it's unsafe. So these are our two examples. Let's use this one to do a fake problem with, okay? So let's see if we can figure out how it works. All I want you to know is how it works. This is kVp, boom, right there. And the lines that are curved, okay, here are all these colored lines, and then here's their representations down here. So we're going to pretend that we have an exposure of 100, let's see if I can write this. Okay, here we go. We have 100. Nope, it's not going to let me do that. Okay, I thought it was going to let me draw. So we have 100 kV. Okay, so we have 100 kV at 1 second, and let me take that off. No, and then 600 MA. So we can look at the chart in the top left of your screen. So here's the 100 kV right there. Okay, so this is the 100 kV. And then seconds and intersect those lines. So 100 kV and 1 second. Now we have to go all the way out here to 1. So it's this line and go up to, there's the 100 right there. Whoops. So there's the 100. So you see where my dot is right there. Now we want to know if we can use 600 MA. So if you go down here, and 600 MA is this one. So it's right here, but there's the line. Where does the 600 MA fall? Our intersecting line falls above the 600, so the exposure is not safe. Now I'll have to admit this one was a little close. So there's 100 right on over to 1. And so that 600 is right above it. So that would be considered unsafe. And remember, most of this, the machines that you use today would be built in, so you'd be okay with that, but this is just one of those examples. So that's just an idea. This may also be something you could work on with lab, and we could go over it some more later if you wanted to. Here's the other one, is a heat unit. So a heat unit means how much heat is actually stored in the device. So you take your kV times your MA times your seconds, and then C. C stands for I'm sorry, the generator type. I couldn't even think there for a second. So if you have multiple exposures, then you multiply by the number of exposures. But if you start with just one, you go with kV times MA times S times the generator. Okay, so there's your formula. Here's where this is. kVp is kilovoltage, MA is milliamperes, S is seconds. C is the generator type. So if you have a single phase, it's just 1. If it's a 3-phase, 6 pulse, it's 1.35, 3-phase, 12 pulse, 1.41, and a high frequency. Again, we'll talk about all those things later. But those are the things that you look at. Now let's look at a problem. If we use 100 kV at 20 mA and 1 second, and then a 3-phase generator. So kV, you go 100 times 20 times 1, and then what is the 3-phase 12 pulse? It is 1.41. So there you go, 100 times 20 times 1 times 1.41, and the answer is 2,820. So 2,820 heat units if we use that exposure. Now, there's something called a cooling chart. Let's go back to olden days. Love to say that. The anode and housing cooling charts both work the same way. So you need to determine the time it takes for it to cool based on the factors given. So the housing cooling chart does the same for the tube housing. So here's our heat units, and then the x-axis is usually in minutes. So the curve that's plotted is the cooling curve. So here's an anode cooling chart, and then here's a housing cooling chart. So they're the same numbers on each side, but the housing itself versus the anode is what you're looking for. So they both work in the same way. Now, if we actually were to use the example that we talked about, and we had the 2080, and we could actually decide how long it takes to get this to cool down. And so if you did this on this one, housing cooling chart, you could, well, the number's not even on here, but it would help you decide what number of, or how long you had to wait before you could use another one. Okay, so it permits the calculations. So you take whatever number that you just got, and this is in the thousands, and then you can go to your minutes. So I don't want to make less of it, but it's not really worth trying to figure it out because it's not something you're going to do in the real life, but it is in your book, so look over that. Okay, here's some simple rules that you need to follow. We have talked about the tube, the X-ray tube, the housing that the tube's in. We've talked about the anode. We talked about the cathode. We talked about how everything works. To extend tube life, simple procedures and guidelines should be followed. If your machine that you're working at, and you'll see this in clinical, they may actually have warm-up steps, and that's specific to the unit, and you should follow them completely and routinely. There are times when it says, okay, our unit says, if we haven't taken an x-ray in 3 hours, we need to warm it up before we take another x-ray, because you could risk cracking the tube. Now, newer units may have automatic, it may have already done that, but if so, make sure that you warm it up just like you should. How many of you, and hey, this is for our Minnesota people, if you have 5 below degree temperatures and you go and crank your car, or you're going to jump right out into the road with it, no, you should let it warm up just a little bit. We don't have that problem as much here in Florida. But the second one is, do not prep the rotor excessively. Every time you prep that rotor, then you've actually warmed it up and you're making the heat build up a little bit more. So the best thing is to press the rotor and the exposure at almost the same time. And then third, do not use extreme exposure factors. With that, that means if you continuously use large amounts of technique or exposure, then you can put damage on the anode. And this is a picture of a damaged anode with burn marks. The anode should be nice and smooth. This isn't. So it wasn't moving like it should, and then it's got these red marks, it's got these marks. Those are not good at all, okay? So you don't want that to happen. Chapter 5, we talked about the text objectives. The things that we talked about, it seems like a lot of information, but I want you to remember the housing of an X-ray tube, why it's important, what is inside the component of the X-ray tube and the operation of each, just like the anode and the cathode. You need to know about the line focus principle, the definition, what is the anode Hill effect, how is the cathode designed, and why is it designed the way it is. Basic circuitry of an X-ray tube. Know what a tube rating chart and an anode cooling chart and a housing cooling chart is, and then be able to employ methods of safe X-ray tube operation so you can extend your tube life. So, I hope that you actually listened all the way through. I hope I didn't confuse you anymore. This is all for this week. I am going to actually do this for every chapter that we have, just because I like talking. And I like to maybe put a little spin on some of the things that may not be as clear, but I need to hear from you also. So this is my little question to you. What do you need more help with? You let me know. Get all your assignments turned in by Sunday at midnight, and I look forward to next week. Thanks, guys.